On land, the versatile forklift is the construction man's jack of all moving jobs. Under the sea, builders and salvage men have always been hampered by the lack of an efficient method of carrying heavy objects from place to place. The answer to this problem may be the Buoyancy Transport Vehicle, BTV. Some call it an undersea forklift. The BTV was developed by the Hawaii Laboratory of the Naval Undersea Research and Development Center. Field testing was done by the Naval Civil Engineering Laboratory, utilizing a test site near Anacapa Island, about 14 miles from the laboratory. The small size and light weight of the BTV allowed it to be easily transported and launched by the NCEL diving support boat, an LCM-8. The simplicity and ease of operation of the BTV are assets in any undersea vehicle. Even with simple vehicles, pre-dive checkout is required to assure safe operations. The horizontal and vertical thrusters, controlled independently by handlebar-type grips, are checked prior to each dive. Vehicle buoyancy is controlled by adding or expelling water from the center sphere using high-pressure air and butterfly valves, one at the top and one at the bottom of the sphere. Air supply and valve position are controlled by levers located immediately above the control console. Power for the vehicle is supplied by 8 52-cell, 100-volt, 12.5 ampere-hour sets of silver-zinc alkaline batteries, which are housed in the 2 upper cylinders. Following a complete vehicle checkout and arrival at the work site, the BTV was launched using a small hydraulic crane. Divers disconnected the lifting slings and moved away to the test site located a short distance from the support boat in about 50 feet of water. To ascend or descend, the diver operator trims the vehicle to neutral buoyancy, then flies it up, down, forward, or backward using the appropriate thrusters. The NCEL project engineers scheduled a variety of test operations to evaluate the BTV's capabilities. For the speed run test, divers laid out a course on the sea bottom. Anchored floats marked each end of the course. A tape was stretched along the bottom between the floats to serve as a guideline. Procedures outlined at the topside briefing were reconfirmed, and the timer moved off to his position at the start of the 100-foot course. The test plan called for the BTV to make a running start. Maximum speed attained during the Anacapa tests was 1.3 knots. Other dives provided data on buoyancy control, maneuverability, endurance, and ease of operator control. These primary tests were followed by a series of dives during which the BTV was evaluated with a variety of fixed buoyancy payloads, covering the range of weights and sizes the vehicle is capable of handling. A baseline load placement test was conducted using a 500-pound steel weight suspended on a wire rope strap from the BTV load hook. Time required for the operator to place the weight on a target and the accuracy of placement were measured. Additional dives were made using a test structure consisting of a vertical cylinder 46 inches in diameter and 79 inches high, with a 40-inch high angle iron base. The structure weighed 936 pounds in water. The object of these tests was to move the structure and place it on a foundation. Again, placement times were measured. Placement of the structure was made difficult by factors such as the small size of the target window, current, surge, and poor visibility. The culmination of the BTV testing and evaluation was an experiment called the DIVERCON BTV Exercise. In this exercise, the DIVERCON 1 structure was assembled using the BTV to simulate the operational construction of a modular ocean floor structure. The DIVERCON structure is made up of 3 ring-shaped modules, forming a 10 by 10 foot vertical cylinder with a dome top. Guide rods located around the top of the lower and middle rings provide translational guidance within a target window that is 1 foot larger in diameter than the ring modules. The last and most difficult part of the assembly was the placement of the dome top. Buoyancy in the form of rigid, constant volume floats supplemented the 1,000-pound lift capability of the BTV, since the in-water weights of the modules were 1,300, 1,400, and 2,000 pounds. After being attached to the dome, the floats were filled with air. Prior to this test, the DIVERCON structure had been assembled 3 times in preparation for the SeaLab III experiment, using a tethered lift device, a surface power system, and a working team of 2 divers. Average time of assembly by this method was 6 hours, 9 minutes. Using the BTV, assembly time was reduced to 1 hour, 45 minutes, less than 1/3 as long. This test program has shown that a small free-swimming lift device is a useful tool for the construction or salvage diver. Such a vehicle provides a capability to precisely position multi-thousand-pound payloads on the ocean floor without surface support at any depths which divers can work. Upon successful completion of the test program, the BTV was transported to the Naval Undersea Center, San Diego, for use as a range support vehicle.